yesterday, because on the eve of our discussion of this future conference, we decided to invite people who are not very close in both in methods and in ideas to what we are doing in physics. This concerns not only physicists with unusual methods like neural networks and so on, but also people who are related to history and in some part to philosophy. Here just I gave the portrait of philosophers starting from, maybe you can recognize some of them. This is Socrates, and the second one should be Plato, but he doesn't want to go out. And these are classical philosophers. So we know that Socrates, he did not write anything, and it was Plato who made public his thoughts about philosophy and any other such things. Now, so this is Immanuel Kant, and I take his portrait not just occasionally, because his thoughts about space and time are related to, tightly related to one of our today's speakers, Olivier, which gives us new entangled relativity point of view to physics. Then I will come back to this subject. Then here is Ernest Mach. Here is Henri Poincaré. Both were criticized by Vladimir Lenin in his famous book Materialism and Empirical Criticism. But nonetheless, he recognized that all of them, they are great physicists and great contributors to the human knowledge. From contemporary physicists, I would like to mention Soichi Sakata, the author of one of the famous model for elementary particle constituents. He tried to use proton, neutron, and lambda hyperon in order to compose all other hadrons. Not without great success, but it was the first illusion to people to invent quark models. But then we see Ernst Schrödinger, and finally Heisenberg. Well, I show not everybody of physicists who were interested in philosophy. They wrote, all of them, I mean physicists which are shown here, Sakata, Schrödinger, and Heisenberg, they were not just a kind of amateur in physics, but also they contributed into creation of some new philosophical idea and philosophical vision of physics. And that's why we think that it's not without use to invite people for today, for example, in particular, who gave talks related to philosophy and to history also. Now, the first speaker who is not seen because of the peculiar properties of the screen, it was Olivier Minazzoli, who presented the talk devoted to entangled relativity. Why I said about him in relationship with Kant? Because it was Kant who said that space and time are but a form of existence of matter. And that's why Olivier Minazzoli, he invented the action in which time, in which geometry and matter are designed in such a way that without matter, no we cannot say anything about geometry. And what I can ask you now is to ask him questions about his talk, if you still remember what did he say in the morning.
Okay, questions to Professor Minatsoli?
No, I will ask Olivier. It is maybe a special question concerning the solutions. If you have some kind of central symmetric solutions, like what's the solution in your approach?
Maybe he is absent.
Huh?
Professor,
I don't know.
Professor Minatsoli, did you hear the question?
Maybe
he seems connected.
Yeah, no. Professor is absent.
He left.
Yeah.
Okay.
No, he has even opened his microphone, but I cannot hear him.
Just listen. Okay, let's.
There is a message in the chat, I think. Okay.
Yeah. Yeah, we can't hear you.
We can. Please. He says something, but we cannot.
Professor? No, we don't hear you. Okay, now we hear you. Yeah.
Sorry, I don't understand what happened. It stopped to work for some reason. Okay, so sorry about that. So yeah, yes, we do have the spherical solution for this theory, black hole solution, although it cannot be vacuum solution, obviously, and therefore it has necessitate matter fields, and so it's a charged spherical black hole solution. Actually, I've talked about it during my talk this morning. And now we also have the slowly rotating black hole solution, charged black hole solution. So that's to answer your question, whether we do have a spherical solution in our theory or not. But I would like just to comment a little bit about what you said. The physicist that liked philosophy, and I would put Einstein as well in the list that you gave to us, because actually Einstein was really driven by principles, and principles are by definition metaphysical, and therefore it's philosophical questions.
Okay, let me precise. When you say about the vacuum solution of the gravitational equations, you mean the literal vacuum? This is a zero on the right-hand side, or some object which is described by maybe point-like particle or something like that. Because if you will put nothing to the right-hand side, you obtain nothing.
Yeah, what I meant here is the classical vacuum, in the sense nothing, void, nothingness.
But with nothing, you will obtain only flat matrix.
Nothing is not possible in the theory. It's not something that you can define, and therefore, and therefore Minkowski is not solution of this theory.
Okay, thank you very much. Sometimes people they say vacuum solution. They are not a vacuum because they mean anything in the right-hand side. Okay, now let's go further.
Oh, I have also a question. Can I ask you?
Yes.
Yeah, sure.
Oliver,
Alexander.
do you have some predictions which are different from predictions of general relativity, which could discriminate between your theory and standard theory of relativity? Thank you.
Yes, thank you for the question. Yes, actually, so the theory predicts that h bar varies with gravitational phenomena. For instance, I shown this morning that for neutron stars, the variation of h bar could be about at the percent level between the surface of the neutron stars and a remote observer. So this is a clear and unique prediction of the theory, and it has no free parameter to adjust. So yeah, this is something that eventually could be checked. Otherwise, last summer, I shown that there is a deviation of the Shapiro delay in the solar system at the C2-4 level. This is a this is a next to leading order effect. So this is too small to be probed experimentally in the solar system with current experiments or observations, I would say, with current spacecrafts. But maybe eventually in a few decades that would be possible to probe this effect as well. And there might be other way to test the theories, because after all, we've been only a very small number of people working on it, and therefore there are many things to be studied and to be checked in this theory. So there might be other way to actually test the theory. New predictions of the theory that has to be found.
Thank you very much.
Thank you for the question.
Wolfgang.
Yes, thank you. First, you mentioned Einstein. I would also add Niels Bohr in particular, although one could add many names, but he was also particularly interested in philosophy. But now, about coming back to the vacuum, we know that in quantum field theory, we have a different Can you hear me?
Yes.
Yeah.
We have a different perspective. We say the fields are always there, and if they're all in their ground states, that this is the vacuum. But of course, that still implies vacuum energy density, which is in principle actually quite high. And then one can see, okay, this maybe causes the Casimir force, but on the other hand, it fails to predict the good value of the cosmological constant. So maybe you can comment both from the philosophical perspective, also from the perspective of entanglement. What is the impact of the existence of vacuum energy density?
Okay. So the formulation of the theory is through its path integral. So obviously you will have the quantum vacuum in the theory. What I would say from the philosophical point of view, it is possible to define general relativity without any matter. And this would be a non-trivial theory at the classical level already, because you could have an expanding universe filled with a lot of black holes, and this has a non-trivial dynamics. So here, what the theory does is that it imposes at the formulation of the theory, at the level of the definition of the action, to have both matter and curvature at the same time. You cannot treat them separately. And this goes inside the quantum phase of the path integral. Therefore, as soon as matter must exist, then you will have matter with the vacuum. The quantum vacuum of matter, of course. I don't know if I answered your question.
Yeah, thank you.
Maybe I can share my screen with my slides, because it might be easier to actually answer to you.
Yeah, I have missed your talk. Unfortunately, for me it was.
Yeah. So let me share my screen. Oh, I cannot share my screen. Because there is someone who is sharing. Oh yeah, because two participants cannot share their screen at the same time.
No, it's not possible at the moment. Okay, it's not
Yeah,
possible.
so basically, let me remind what the theory does. So basically, it's a nonlinear reformulation of the action of general relativity, where instead of having a linear coupling between the Ricci scalar and matter fields, you have a nonlinear coupling between the two. And this nonlinear coupling is such that if matter does not exist, then the whole theory does not exist. And this is why we named it entangled relativity. It has nothing to do a priori with quantum entanglement, but it means that you cannot treat gravity on one hand and matter fields on the other hand separately. They must be considered at the same time. But nevertheless, what we've shown is that the theory converges, gives back general relativity in some limit, and gives back the usual standard quantum field theory in the same limit.
Okay.
Okay, if no more question to Olivier, we continue.
Thank you very much for your
It was
questions.
Presentation
For the invitation.
by Valentin Zakharov, the theory of gravity in the limit of Newton's constant, tending to zero. 2 words about that from my side. It seems to me there is some kind of misunderstanding in this field, because the people, they believe that the equivalent principle is just identification of non-inertial frames and gravitation. It's absolutely not true, because the forces are quite different order. I mean, in so-called inertial forces, they may be eliminated by the change of frame. But nonetheless, the people, they prefer such a name. But again, I want to stress that theory of gravity has nothing to do with what discussed in this work, which is itself is very good, certainly very good, and its prediction can be checked experimentally. So if somebody has questions to this talk,
Raise questions to the talk by Dr. Zakharov.
no. And he talk, he's absent also. Okay, he's not very much interested, so we continue. Then Dr. François Pris, contextual realism and physics. It's very difficult to me to comment. If somebody in the hall may say something about what was said, because as I said already, for us who are present physicists, it's very difficult to manipulate with terms like ontological and so on. And so I cannot add something to that, and maybe somebody from the audience can say about Dr. Pris' presentation. No. Okay. Huh? You asked, but maybe we don't know. Maybe we'll ask again. But he's not here, I believe, no? Okay.
I already not here.
Roman Rogalov is here. Okay. He made very interesting presentation concerning the heavy ions with all these temperatures, chemical potentials, and baryon production, and so on. If somebody has questions to him, because I already asked him something, if you want, I can ask more. But maybe somebody in the audience want to say over there.
Can you repeat your statements about comparison between experimental results and theoretical latest predictions?
Latest results on baryon number not expressed in terms of cumulants of net baryon number distributions leads to the scenario of collision as follows. Fireball exchanged by net baryon number with remnants of colliding nuclei until freeze out. And this conclusion contradicts to the statement justified by Ali's experiment that the chemical potential and therefore the net baryon number density in central rapidity region equals 0. 0 net baryon number density in the central rapidity region implies that there is no exchange of fireball between fireball and remnants of colliding nuclei.
Okay, thank you. So if no more questions to Roman, we go further. And Mikhail Sergeyenko, he told us about Schrödinger equation, because it was very interesting, because I thought, because what new can be about Schrödinger equation, but nonetheless he found some new features of the solutions to the Schrödinger equation, and in this way I allow myself to relate with him the citation from the composer Schoenberg, that great deal of things may be already done. This is something like in this way, so it's very pleasant. Okay, if no questions to him concerning his solutions to the Schrödinger equation, no. So
yes, I am here, and I would like to make more clear my conclusion to this report. Can I make, because there is not so clear from the screen, and I couldn't make my conclusion clearly. Let me repeat my conclusion to this work.
So what?
I'd like to make just comment to my conclusion.
Yes, do.
Okay. Conclusion to this work is, we have shown that the Schrödinger wave equation can be derived using the classical action. I mean, the Hamilton principal function. It is the key object in our approach. In our approach, there is no place for the concept action in quantum mechanics. Second, we have obtained the Schrödinger equation in the phase space. Third, we have derived the connection formulas and the phase space in the phase space using which we obtained the exact quantization condition for two turning point problems. Fourth, the general solution of the obtained equation is given by the superposition of two plane waves in the phase space. Fifth, we have generalized our approach for three-dimensional Schrödinger equation. The same simple rules and general solution formulated for two turning point problems can be applied for multi-dimensional and multi-turning point problems as well. This approach can be easily generalized for the non-separable problems. Our approach can be considered as a general method for solving the Schrödinger equation, because there is one form of the solution for all types of problems and potentials, the same. And this solution just coincides with the asymptotic of the exact solution of the Schrödinger equation. In fact, I have obtained just asymptotic solution directly from this equation. I derived and obtained the just asymptotic solution without obtaining the exact solution.
Very good. Very
In
good.
that sense, I think that this kind of asymptotic solution can be considered as kind of exact solutions.
But you should repeat your talk already.
Yeah, because they do exact eigenvalues for non-solvable potential.
Okay, thank you very much. Thank you. Thank you. We believe that you have found some new ways, and we wish you all the success with that. So we go further.
Yes, yes. I hope.
Now I come to Alexander Panov, who presented us a very interesting talk related to physics, mostly in connection with cosmology and so on. I don't know who said, you or somebody else, who said that something against Popper. It was you? That somebody said that a Popper, you said, so you are against falsification. Okay, because somebody, maybe you, maybe other person said that the Popper falsification principle is not good, so we have to reject it and take something else instead.
My opinion is the principle of falsification of Popper is that thing that distinguish what is science from what is not science, because science is only those kind of minds that produced verifiable results, and falsification is a concentration of this idea, the presence of falsification. It is impossible to prove that this principle is correct. For my opinion, we can only admit or don't admit it. It is each investigator should should produce its own choice, admit or don't admit this principle.
Okay, but I thought that he said no theory can be true. You should always test the theory till the end.
Yes.
Then will you find that it is not true. This is a process of falsification.
Yes.
Actually, what is done normally in practice of physics, no?
I think that science don't produce proven or absolute falsifications of any results. I think that science produce only more probable results. If the probability of results grades strongly, then they can say about proven in some sense. But if the probability of some results became to decrease, we can say about falsification, and all these proposition is only approximations.
Good, thank you very much. Let's
Okay, a question.
leave alone.
A question from Wolfgang.
From Wolfgang.
Okay. I will be brief, just a comment. You're right, one cannot prove, of course, the principle, although it sounds reasonable to me what Popper suggested, although rather trivial. However, still, I would say science in reality doesn't work this way. So that we make a proposal, a hypothesis, and if it fails, then we reject it and exclude it. In reality, what happens very often is that then people modify it and tune it and try to adjust it to the data. For instance, we have not seen supersymmetric particles. Now we can move the masses up and say maybe they are heavier. We haven't seen it. We haven't seen axions. Okay, we have problem with flavor changing neutral current. Then we say, okay, the coupling varies very slowly. Then maybe we can avoid this problem. So in reality, it's not that the community rejects anything which is not which is falsified, but rather that it modifies it and adjusts it. That this, I think, this Popper has not taken into account. Thank you.
Okay, thank you. If somebody wants still to ask Professor Panov here or there,
No.
nobody. Okay, so let's go further. And I cannot go further again. Maybe no, it still work. Huh? So I just open everything in order not to have problems. Okay, good. Now Professor Nakamura, he tell us told us very interesting things about quantum computers, many prospects, and so some bright future expects us with these new devices. Concerning the lattice quantum theory, for me, what was very interesting to know that some progress is expected in the field of lattice theory with real time. That's very good because we're already tired to deal with four-dimensional Euclidean space. And if we would be able to obtain results from our colleagues in Minkowski space, it would be very nice. Good. Now, Paul Tappenden said about wave function as a concrete object. I had some question to him, but already forgot. Maybe we'll remember. What did he say? Okay. Huh?
He is absent.
But yes, anyway, he is absent. We'll remember about that. So Vitaly Vanchurin, I was awfully astonished that people, I mean that there is not only him, there is the whole tribe of these people or sect or I don't know what, because they say that that everything is emergent. Lorentz symmetry is emergent, quantumness is emergent, Maxwell equations are emergent, everything is emergent. Huh?
Time is emergent.
Time also is emergent, yes, everything is emergent. So, but starting what from? What is the most important, most fundamental that these things which are emergent? Okay, and I can ask, I believe that he already left maybe. He is present, Vitaly. So I would like to ask, so if your underlying entities like learning neurons, something like that, because anyway you put some facts about them, so if they are given to us as something fundamental, why we should be guaranteed that nothing under them also can be found in future?
All right, so that I can answer, right? Yes.
Yeah, Vitaly.
Okay. Yeah. So there are two questions here. Why is everything emergent? Now, of course, it's not true. Not everything is emergent, but as we're well known, classical physics is emergent from quantum physics. Nobody questions that. It emerges in a certain limit. Thermodynamics is emergent. It emerges in a certain limit. And in physics, we're dealing all the time with emergent phenomena, not because we don't like how things work on the fundamental level, but because sometimes it's very often, it's very difficult to do true calculations using microscopic quantities and following the dynamics of every single microscopic object in detail. So this is not because we don't like fundamental description. It's because we don't have the ability to do that. That's defending everybody who is studying emergent phenomena, including all of the people who study thermodynamics and classical theories. Okay, so now talking about what is and what isn't fundamental in this particular neural network theory or any other theory, you do have to assume what is fundamental. Now, if you're working in the realm of field theories, you make assumption that fields are fundamental. Okay, you do not ask questions. What are the fields are made of? If you do ask these questions, then you have to go deeper and make other assumptions. For example, you can assume that strings are fundamental, and even field theories emerge from that, and that's okay, as long as you're explicit. Is what is it that you assume fundamental, and as long as you show calculations when other objects, other emergent descriptions are useful, you're good. Okay, good, general. Now, in this particular theory, it is an assumption that the learning dynamics of neural networks that are very well defined mathematically, so there's no question of that, is the fundamental object. From that, you may or may not be able to see how this system behaves on a macroscopic scales. Sometimes it's easy in certain limits, in certain limits it's hard, in yet other limits it's just impossible, and you have to do simulations. But so is true in any other physics theory. something is assumed to be fundamental, then you do some approximations and study how it behaves in the emergent picture. Now, if you don't like the word emergent, think macroscopic, equate the two things. If you don't like macroscopic, think about thermodynamic description. Whatever it is, what you know that the degrees of freedom and the relevant variables that were at the macroscopic scale are no longer relevant for that description. Okay.
I had an impression, maybe may I ask you, I had an impression that at the level of this neuron mechanics of physics, you take anyway the classical statistical theory because you take the Gibbs distribution and so on, and temperature.
You don't.
Notions, no?
Right. So the classical statistical physics can be taught by postulating a certain distribution. So that if we are
okay, I see now.
Instead of that, what you you don't have to do that. What you can do is postulate the maximum entropy principle. Then there is no physics assumed. You're just dealing with a probability distribution. You impose a constraint on whatever property, and then you make derivations. So there's no assumption of physics, statistical physics, classical physics, quantum physics is needed. But of course, the tools of the probability theory are everywhere. And so we cannot just throw away mathematics.
You expressed for example, you expressed the Planck constant via parameters of the Madelung equation, quantum hydrodynamics. Why do you think that these parameters are more fundamental than the Planck constant? I can do.
Well, when it comes to the Madelung equation, this is definitely not fundamental, and it is a wrong equation. It doesn't give you the quantums, okay? So Madelung equation that you get from the approximation the learning dynamics is not quantum mechanics, okay? It doesn't have the multivaluedness. It doesn't have all of the things. It doesn't reduce to a Schrodinger equation. So no, you should not equate those. Madelung equations definitely not more fundamental. There is no way you can start with a Madelung equation and derive Schrodinger equation without making additional assumptions. But the approach here is different. You do not start with a Madelung equation. You start with the neural dynamics of neurons. You see that in certain limit, meaning for certain algorithms of certain systems, the Madelung description is correct, not quantum, but the Madelung. And in the other limits, where you're dealing with the grand canonical ensemble of neurons, other description is correct, which is a Schrodinger description. So in this picture, Madelung definitely not more fundamental, but neural dynamics is more fundamental, of course. Now, is it equal to quantum mechanics? No, I've emphasized it that these calculations show exactly when the quantum description should break down. First of all, if you don't have a bath of neurons. Secondly, if the algorithm is not clever enough to tune its parameters. And thirdly, if you have small enough number of active neurons. All those three limits will just show you that the quantum description is just wrong to describe it. Now, if it turns out that the universe is such that the quantum description is exact, then of course this theory would have to be wrong.
Okay, thank you very much. I believe that you are maybe on the very new track, very bold, very brave. I have to wish you all the success. Well, I keep some reservation about that, but it's
that's normal.
Okay.
Thanks.
Now, Professor
Евгений
Bianchi, he presented us very interesting things about some kind of geometrical considerations related to loop quantum gravity and quantum information as well. While if somebody have questions to him.
Questions to Professor Eugenio Bianchi?
Yes, Alexander.
I have a general questions about loop quantum gravity. Why it is meaningful to study quantum geometry apart with accounting for of quantum fluctuations of all other fields, because it seems that we must locate it the quantum fluctuations of all other fields in at right-hand side of quantum Einstein equation, and then this quantum fluctuation should produce very great fluctuations of quantum geometry. Do you understand my questions? Why we can ignore all quantum fluctuations of all other fields?
Good. Thanks for the question. That's an important point. And I would distinguish two aspects. One is we know quite a lot about quantum theory of matter in terms of quantum fields on a given space-time. And the ultimate goal is to understand quantum geometry and quantum matter together, as you are saying. So there is an intermediate goal of understanding quantum geometry alone in a world without matter, because it's already a non-trivial problem. It's the analog of understanding vacuum general relativity. Now, there's a more important question that I understand it's the one that you are asking of, is there any regime where pure gravity captures the relevant phenomena? Because after all, in cosmology, we do have both gravity dynamical and matter dynamical, and they are both important. So is there any regime where we expect that we can essentially neglect the effect of matter because the dominating effect is purely gravitational, purely quantum gravitational fluctuations? And the expectation is that this happens every time you approach the Planck scale. There's a number of arguments in favor of this scenario. This is a scenario. One is consider black holes. For instance, the entropy of a black hole is purely expressed in terms of the geometry independently of the number of matter fields. Consider this other example. Imagine falling inside a black hole together with matter and quantum fields. When you approach the singularity, or when you approach the Planck's curvature region, all of the effects that dominate are gravitational effects. And this is a statement that comes from the Penrose singularity theorems. You can put whatever matter you want. No form of matter is going to change the approach to the singularity. The fact is that matter contributes always in a way such that even if the pressure increases, and one would say this is going to stop the collapse and produce the singularity, pressure itself gravitates and makes gravity win. I can give you another example, the approach to a cosmological singularity. And when I say singularity, I really don't mean the mathematical singularity. I mean approaching physically a curvature that is as large as Planck curvature. And there again, one expects that gravity dominates all of the quantum fluctuations. There's a classical version of all this that is the BKL conjecture, the Belinsky-Kalashnikov-Lifshitz conjecture. That is, you can really neglect all contributions of matter into approach to a high curvature regime. And so in this sense, in loop quantum gravity, we do have vacuum loop quantum gravity, and you can and you have to put matter in loop quantum gravity. We know how to couple it to fermions and gauge fields. But even the theory without matter is relevant for these regimes that are high curvature regimes.
Okay, thank you. A question from Professor Minazzoli. Professor Minazzoli?
Yes, can you hear me now?
Yeah.
Okay, thank you. So actually, it's not really a question to Eugenio, but more a comeback to my own talk, which is related to what just has been discussed. But I want to stress that if entangled relativity has anything to do with reality, then it means that quantizing gravity alone would not even be allowed. It wouldn't even make sense to do it in this framework. So of course, provided that this framework is correct and probably not. But I wanted to stress that because I think it's really important. It's related to the question that has been asked to Eugenio. Another thing that I would like to add respect to that is that because the theory predicts that h-bar can vary depending on gravitational phenomena, it means, or it seems to indicate, that a canonical quantization is not valid all the time. And probably it means that canonical quantization can only be used as an approximation in the limit where h-bar is a constant. And otherwise you have to think through the path integral formulation only, meaning that probably, but this has to be checked, that in this framework, you lose the equivalence between the path integral formulation and canonical quantization. And this is something that I forgot to say earlier, but because it was somehow related to what is now discussed, I wanted to stress that as well. Thank you.
Okay. Thank you.
Good. So if no other questions to Bianchi, and now we come to the last, not least, presentation by Professor Bietenholz concerning the dissemination of lattice studies all over the world. Honestly speaking, I always during his talk, I tried to follow where Russia is. Unfortunately, it was not always on the first places, but somewhere maybe in second half. But I was particularly glad to see that Benin also is in this game. It's very good because Africa should join to other continents in lattice studies. Maybe the lattice physics is the only physics which is now popular in Africa. That's very good. My congratulations to lattice colleagues. Very good. If somebody has anyway questions to Professor Bietenholz, please do that.
Wolfgang, can you formulate what are the main main essential changes in the data you presented over the years, both for Heplet and for average data over 7 categories of archive?
Yeah, first of all, I fully agree with the previous comment. I would like to say I was also happy to see Benin showing up there. Now about the second question, as I said, I was actually surprised myself that since about 98, the lattice community is stagnating in the sense of productivity. Doesn't mean that it doesn't do anything new, of course, everything is new, but just the productivity is stagnating. Whereas in other fields like HEP-TH, HEP-TH sections and so on, or gravity particularly keeps growing. So I'm not sure what this is based on. I can just I think interpretations are always risky. So I prefer just to give the data. And it has certainly, as was also mentioned before, spread over the world more than it was in the beginning. This is what I was told when I was in Mexico, where people never looked at it because they thought this is only for the most wealthy countries which have supercomputers and so on. But this is certainly not true anymore. Computers are all around the world. There are countries like India, China, Pakistan, and so on joining the lattice activities. And nowadays you can, maybe, as I said, we cannot compete with high performance lattice QCD, and there the simple things have all been done already. But there are a lot of other conceptual projects or in lower field theory in lower dimensions, but where topology is relevant and so on, where one can also contribute. And we hope to convince more people that this is a robust method, gives explicit results, not only conjectures and so on. So I think the evolution is still that it very gradually spreads to new countries, which also join our field and our activities. And I'm glad to see that. And I think even for students, we know that most students who write a thesis do not stay in physics later, but it gives them a good preparation, even if they later they work somewhere else, but they know how to program, how to analyze data, and so on. And I think we should promote our field more, and this is gradually happening.
Okay,
I
thank
don't
you very
know,
much.
have I answered the
Good.
question, or?
Thank you.
Okay, no more questions. So we shall, it remains to us several minutes. I want to show some more slides a little bit. And this sculpture, I have chosen it just to illustrate my feelings when I try to imagine the world as a neural network. It's very difficult. It's very difficult to imagine, but nonetheless, I will try. Okay. So, давай ее следующий можно как-нибудь продвинуть? In the beginning of this workshop, when I... А там нет ничего больше? Там есть. Okay.
Would I have to comment on that or no?
Нет, там был следующий слайд. Его нет. Okay. This is just the reminder that when I heard about many unusual things related to quantum gravity, triangulation of the world, and so on, some thoughts arose in my mind, and I want to warn that in this field is very dangerous actually. And if you want to know what are the dangers in this business, I recommend you to write down to read this book by Alain Sokal and Jean Bricmont. It was written in '97, and it was recently, not very recently, but there is a Russian translation of it. And in this book, you will learn very interesting things about scientific fraud, etc. I don't want to say that our speakers make some kind of fraudulent, not at all. But nonetheless, sometimes it seems to me that we are very close to it. Okay. Now, in the beginning of our conference, our meeting, I have shown you the failed project of the Proton Collider at 6 TeV proton, when we hope to discover maybe even Higgs here. It was failed, and as a sign of this failure, I showed this picture. But one of the participants, Professor Serebrov from St. Petersburg, said me that we should be so pessimistic about the future of Russian high-energy physics, and he advised me to change the crow to the dove, and the dove of peace, and road to the future. Let Collider is closed, nothing to say about that. But there are other things. And he suggested us to join to the searches for sterile neutrino, which they do with a reactor in Leningrad, in St. Petersburg. And also, if we take our accelerator, the booster, so joint work in this direction will be fruitful. Okay, now let me just remind some saying from some cynical person who said that attending the scientific conference is very good because afterwards you feel that you are not the only fool in the world. So farewell and good luck, and thank you very much for coming and presenting your talks. Thank you.